Okay, good morning everybody. It's a great pleasure to welcome you all for this 2-day workshop called Enriching Collegiate Mathematics. There is no formal inauguration ceremony or anything like that. We value your time very much, and so we straight away launch into the academic program. There'll be no formal introduction of the speakers for each separate talk, and no chairperson or anything. And so I take this opportunity to sort of introduce all the speakers for today. Professor Amritanshu Prasad, he will give the first talk, first of a two-part talk on linear algebra. Professor Vijay Kodiyalam, he will talk on algebra. And the last talk today will be by Professor Anirban Mukhopadhyay. He is also my colleague. All of us, all the speakers are from this institute. Before I ask Amri to give his talk, may I request you all to put your cell phone in the silent mode, please. Okay, so Amri will now take over.
Since this board is quite small, you may have trouble seeing it from the last row. If that is the case, please feel free to come to the first row. I'm just going to talk about something which most of you would be quite familiar about, namely canonical forms for matrices. It's just something very basic, but I thought that thinking about it carefully may help us understand certain concepts better. So suppose you have linear transformation. Can you read this? Yeah, otherwise you can come forward. So suppose you have a linear transformation T from a vector space V to a vector space W. That just means that T preserves takes T of A1 Ax plus By is Atx plus Bty. So if you have a linear transformation, and suppose you fix bases, so E1 up to Em, that's a basis of V, maybe I want to say En, and F1 up to Fm, that's a basis of W. Then given this much data, a linear transformation, a basis of the domain and a basis of the codomain, you can associate to T a matrix. That is, you look at T of Ej, okay, that's a vector in W. So you ask, what is its expansion with respect to this basis? And you call those coefficients Aij. So Aij Fi, summation I goes from 1 to M. Then this Aij is called the matrix of T with respect to these bases. Okay, so linear transformations are conceptually nice, but when we actually want to work with them, it is more useful to use bases and then get matrices. So it's good to be familiar with both these points of view. They are the same thing. Now let's just examine what this is a little more closely, what is happening here. One way to write this is to say that suppose I take the vector, now this is a vector whose entries are themselves vectors, Te1, this is a vector in W, right? Te2, this is also a vector in W, Ten. So that's a row vector whose entries are vectors, and we can write this identity here as this is equal to F1 Fn F1 Fm times the matrix A. Right, if you think about it, when you multiply this row vector by this matrix, then you are getting F1, so the answer will again be a row vector, and its jth entry will be precisely this Aij Fi. So, this is the same as this, but there is another way of thinking about this in terms of what does t do to the coordinates of vectors. So, suppose you take a vector in V, then you can expand it in terms of this basis and you get coordinates. So, V becomes V1 E1 plus V2 E2 plus Vn En, and then we will ask what are the coordinates of Tv in terms of the basis F1, F2, Fm. So, then Tv, well, that is T of summation j goes from 1 to n Vj Ej, but because of linearity we can write this as summation j goes from 1 to n Vj T of Ej, but T of Ej is given by this formula. So, we can write this as summation j goes from 1 to n summation I goes from 1 to m Vj, I will write it like this Aij Vj. Now, this is nothing but if you take the matrix A, sorry, times, thank you, it is also here, times Fi. And maybe it is a good idea to now interchange the orders of summation. I will write I here, and so the coordinate of the Fi is this thing, and suppose we call this Wi, then what we are getting is the coordinates of T V, namely W1, W2 up to Wm, are given by the matrix A multiplied by the column vector V1 Vn. So, that is another point of view on the matrix. So, there are two ways of thinking about this matrix. One is as it does something to the vectors, the other is it does something to the columns, to the coordinates, and what it does to the coordinates is right multiplication by column vectors. What it does to the vectors is can be represented by this left multiplication by a row. Okay, now this is just to remind you of some very basic things about matrices and linear transformations. Now let us get to what I really want to talk about, which is canonical forms. So, so if you have a vector space, there are many different choices for bases, right? And what happens to the matrix if you change this basis or if you change this basis? What will happen to the matrix A? That will also change. How will it change? So, for example, suppose we have a new basis F1, F2, F prime 1, F prime 2, F prime m of W, then each Fi can be expanded in terms of the new basis. So, I can write Fi equals summation k equals 1 to m, let us say x ki Fk prime. So, this is my new basis. Since it is a basis, I can expand each vector in the old basis in terms of the vectors in the new basis, and I get some coordinate coefficients, and I can arrange them in a matrix. So, this will form an X, a matrix I will call X, and this identity can be represented in the following form: F1 Fm is equal to F1 prime Fm prime times X. Okay, and we can also go the other way. Given we can take each f prime I and expand it in terms of the f case, and we will get a different matrix. That matrix will be the inverse of this matrix X. So, the thing to remember is that this matrix X has an inverse, and therefore, it is a non-singular matrix. It is not just any matrix, it is non-singular. Okay, and we also want to transform the change the basis E1 En, and here I will choose a slightly different convention. I will write Ej prime in terms of Ej. So, Ej prime is summation L goes from 1 to n y L j Ej. So, this is now a new matrix, and again this vector y, this matrix y will be non-singular, and what I can write this as is E1 prime E n prime is equal to E1 En times y. Okay, so, we have got these transformations. Now, let us try to write down the matrix for T with respect to the new bases F1 prime, Fm prime and E1 prime to En prime. So, what we will try to do is to see how we can. So, what we need to do is to write down the matrix. We will take T E1 prime, T E2 prime, T En prime, and try to find some matrix that will fit when we write here F1 prime, Fm prime. But this, if you think about it, because of this identity, this is nothing but Te1 Ten times x. This is because of that identity and the linearity of T. Sorry, times y. See, T E1 prime, I will just show you quickly. T E1, what is E1 prime or Ej prime? T Ej prime is summation L goes from 1 to n. It is T of this, but by linearity I can pull these coefficients out. And this is exactly what I have written here. Okay, so, if you look at the jth entry here, it will precisely reflect that identity. Okay. But this guy we know from here, so that is F1 Fm times A, and I have this y here, right. And then this we know in terms of F1 prime, Fm prime. So, this is the matrix we get. With respect to the new basis, the matrix of T has changed to x times A times y, and this x and y, they are non-singular matrices. Okay, so, two matrices represent the same linear transformation with respect to different bases, if you can write it like this. So, we will define this as an equivalence relation. So, it is the same linear transformation, it is just chosen a different basis. Definition: A is equivalent to B if A and B represent the same linear transformation but with respect to different bases. Linear let us say T from V to W with respect to different bases of V and W. So, any property of that linear transformation which you can interpret in terms of the matrix will be the same for equivalent matrices. For example, I will come to that in more detail. If you have a linear transformation, you can talk about its rank, and if you have a matrix, you can talk about its rank. And it turns out that the rank of the matrix is the same as the rank of a linear transformation that it represents. So, it follows that if two matrices are equivalent, they have the same rank. So, this okay, so this is clearly an equivalence relation because you can I will let you think about that. Now, the problem is this, the main okay, and what we have seen just now is that A is equivalent to B if and only if B is x a y for some x y non-singular. I actually showed only that if A is equivalent to B, then B is x a y. But if B is x a y, then you can define your new coordinates using these formulas and then show that there is a different basis with respect to which the matrix is B. So, this is an equivalence. And the problem that we want to solve is, given two matrices A and B, actually I will write down two questions, one given A and B, presumably of the same shape m by n matrices, determine whether A is equivalent to B. In this case, we want an algorithm. I give you two matrices, this is either true or false, either A is equivalent to B or not. Can you do something to these matrices and tell me for sure? And the second question is, how many or what are the equivalence classes? How many is also how many sort of implies that there are finitely many, or well, I guess they could be infinitely, but maybe a better question is okay, let's just write it like that. How many equivalence classes are there? This is a very typical kind of classification problem in mathematics. You are given certain objects, you are say okay, you have some notion of equivalence, really how many different ones are there? So, and one way to tackle such problems is to use canonical forms. So, the idea is that you will find so what is a canonical form? In abstract, so a canonical form, and we will try to find this, is a collection C of matrices such that every matrix A is equivalent to a unique matrix C in C. Okay, so suppose you can find such a collection, some collection of matrices such that every matrix A is equivalent to a unique matrix in this collection C. Then what you do is, and you can also find some algorithm for finding out this matrix C. Then if you want to know if A and B are equivalent, you find out whether the C in C which they correspond to are the same or not, and you will have answered the first question. And to answer the second question, you just see how many elements are there in C, because each equivalence class has exactly one representative in C. Okay, any questions? Okay, let me just review what I did so far. We talked about linear transformations. When you have a linear transformation, you can write down a matrix, provided you choose a basis for the domain and the codomain. Now, you can change the bases, and then the matrix also changes, and it changes by this formula B equals x a y, where x and y describe how you change the bases. Now, I have erased that exact description, and so we define two matrices to be equivalent if they represent the same linear transformation with respect to different bases, or in other words, if B is equal to x a y for some non-singular matrices x and y. And now what we want to do is we want to classify the equivalence classes. And I am suggesting that we use canonical forms. If it is not clear what I mean by this, it will become clear in a moment when I try to, when I compute these canonical, this tell you exactly what these canonical forms are. So, one technique for reducing matrices to canonical forms are row and is this thing of using row and column operations. This comes from certain special matrices called elementary matrices. So, what is an elementary matrix? Let me just give you some examples. So, you take this matrix 1 1 1 on the diagonals, and then at the ith place you put alpha and then 1 1 1. This is a square matrix. Okay. So, this suppose you have a matrix A and you multiply it on the left, let us call this matrix I x. So, ith row and this is ith column. This alpha is in the I comma ith place. Okay, so suppose I take A and multiply it on the left by x. Okay, so I take A and multiply it on the left by x. Can you tell me what was this matrix x A, how you can write it down from A? Almost correct. So, except you should have said ith row. Yeah. So, this we can write as Ri gets transformed to alpha times Ri. Okay. So, certainly A is equivalent to Xa, because I can take Y to be identity. So, every matrix is equivalent to the matrix obtained by multiplying any of its rows by a non-zero alpha. If this is 0, then this is not non-singular. There is another thing you can do A goes to Ax. I am being a bit careless here, of course, because the size of this x would have to be different from the size of this x if A is not a square matrix. If A is m by n, then this should be m by m and this should be n by n. But never mind, this would be ith column goes to alpha times ith column. Okay, so this is the first type of transformation. It's just taking a row and multiplying it by some constant, and let's assume that alpha is not equal to 0, otherwise this matrix will not be non-singular. Now comes my favorite matrix. Now you just put 1s everywhere on the diagonal. These entries are all understood to be 0. So if I don't write any entries, just assume they are 0. And then everything is 0, 1 here, everything else is 0 except in one place alpha, I will put this is the ith row and this is the jth column. Now if you take A goes to xa, what is happening? So if you think about it, you have your matrix X written down here, and if you take a row where this alpha does not occur, then when you are multiplying it, you will just here you will be writing x11 itself, right. So if you take a row where this alpha does not occur, those rows will remain the same. But this this row, what will happen is that you will end up taking the ith row will change, and how will it change? Can you tell me? So see, let's just see the ith row. So here I have xi1, xi2, xin. Oh, sorry, that's not. Yeah. So when I'm looking at the jth column, so when I do it, I'll get xii. Actually, I guess I want to look at the. Yeah. Right. So is this correct? So you are taking the ith row and adding to it a scalar multiple of the jth column. In this case, alpha can be 0 also, this matrix will still be non-singular. But if alpha is 0, you are not doing anything at all to your matrix. And there is another thing you can do, you can take A to Ax, and this will have some effect on the columns, and I will leave you to work it out later if you like. But what this does is, the jth column goes to the jth column plus alpha times the ith column. So what you can do is you can take some row and add to it a scalar multiple of some other row, not the same row, and you can take some column and add to it some scalar multiple of some other column. And these are again equivalent matrices. So if you do any of these operations, your matrices remain equivalent. And finally, there is one more operation which is used, and that is now what you do is you take identity, one along the diagonal, but at two places, let us say this is the ith row and ith column, and this is the jth row and jth column, ith entry, jth entry. Instead of ones, you put zeros. And where do you do, what do you do to these ones? You put them like that. So what you have is the I comma jth entry is 1 and the j comma ith entry is 1, but the I comma ith entry and the j comma jth entry are zeros. and apart from that it just looks like the identity matrix. So this is a matrix with, okay, so if you take x times A, what happens? So if you take A goes to x times A, then just think about it. When you are computing any entry, you will be taking the, if you take some row which is not I or j, nothing happens, because it is just going to hit this 1 at the ith place. But if you take some other row, what will happen is in the ith row you will get the jth row, and in the jth row you will get the ith row. So what will happen is the ith row gets interchanged with the jth row. And if you do A goes to Ax, then the ith column gets interchanged with the jth column. Okay, and then these matrices are still equivalent. So you can interchange two rows, you can interchange two columns, you can scale a row, you can scale a column, you can add a multiple of one row to another, you can add a multiple of one column to another, and you will still get equivalent, a matrix equivalent to your original matrix. And you can do these operations one after the other. And now using these operations, let us see if we can reduce any matrix to a very simple form. So the one form that is used is called the echelon form. Every matrix can be reduced to one of these forms. So let A, maybe I'll call it Ci, this matrix. So there's 1, 1, 1, 1. This is I ones. Maybe I'll write it as identity matrix I by I. And then 0, 0, 0. This is a block matrix. Okay, whatever space is left, you fill it with zeros. Call this Ci. Then this is called an echelon form, and this every matrix can be reduced to one of the matrices Ci by elementary row and column operations. Let us see how to do this. So basically what you want is you want ones along the top left corners. We will do this by induction. You start with some matrix. This I can be 0 also. So C0 is just the 0 matrix. Don't forget. So now you have some matrix, you have some matrix A, and it has some entries. Now what I want to do is I want to make this thing 1. That's the first thing I want to do. Yes. This matrix. Yes. No, the notion of equivalence here is different. There's no, yeah. So there the determinant can change. Yeah, maybe there are different uses of the same terminology. So don't worry about what I'm calling this form. And let me just call it canonical form to be safe and not confuse you. And okay, so the determinant can definitely change. So this need not have the same determinant as the originator. So, and I'll show you now that we can do this. So you want to make this 1. So if it's not 0, then you can always multiply it by something and make it 1. But if it is 0, then you need to do something else. So suppose you have 0 here. Now if your whole matrix is 0, then it's already in canonical form, it is C0. So suppose, so you're done. But if the whole matrix is not 0, then somewhere in this matrix, say here, there is some entry which is not 0, say you have 5 or something here. Then what you do is, you interchange the third row with the first row, then this 5 comes here, then you interchange the first row with the second row, then that 5 comes there. So by interchanging rows and columns, you can make sure that this thing is not equal to 0. And once it's not equal to 0, you multiply the first row by some appropriate constant and make this equal to 1. So what you can do is you can make this equal to 1. Now once you've made this equal to 1, you can make all these entries 0. How? Suppose you had, instead of 0 here, suppose you had 5. Then you take the second column and subtract from it 5 times the first column, and then it will become 0. Okay, it will change all these other rows, but it's okay, let's not worry about that. And similarly, you can make the first column also 1 0 0 0 by subtracting appropriate multiples of the first row. So now this first row and first column have been made correct. And now you look at this submatrix, slightly smaller matrix. And now you do the same kind of thing. Suppose this submatrix is 0, then you're done, you got C1. Otherwise, you find some non-zero entry here, and by interchanging only among these rows and these columns, if you do that, you won't be moving this 1, right? You can bring the 1 here. You can bring a non-zero entry here. Then by scaling the second row or second column, you can make this 1 again. And then by subtracting multiples of this column from the other columns, you can get zeros here again. And that none of those operations, you must note, will disturb the first row or the first column. So you can do this, and after a finite number of steps, you will end up with a matrix like this. Okay, it's quite possible that this identity will fill up all the rows, so this part will not be there, or it will fill up all the columns, so this part will not be there. Okay, but in any case, you will end up with something like this. So every matrix is equivalent to Ci for some I, and I can be anything between 0 and the minimum of m and n. It cannot be more than m or n, because this has to fit inside the m by n matrix. And but then there is always the question, is it possible that C3 is equivalent to C7? It could be that you can do the reduction in one way and get C3, and you do the reduction in some other way and get C7. Then this would not be a useful canonical form, because the same matrix can be C3 or C7, then you can't use this to decide whether two matrices are equivalent or not, because they may be equivalent, but then they may give you different canonical forms. So we need to make sure that if Ci is similar, equivalent to Cj, then I equals j. Is this true? And this is where the notion of rank comes to the rescue, as I was saying earlier. So what's the rank of a linear transformation? So let's come back to T. So if you have this T, you can look at the space TV, V belongs to V. This is a subspace of W. This is a linear subspace of W. It's closed under scalar multiplication and addition. and rank of T is defined as, so I will call this T of capital V. Rank of T is defined as dimension of TV. And if you look at the, if suppose A is the matrix representing T, then the coordinates of the vectors in TV so it's summation W. Now I keep forgetting, it should be I goes from 1 to M W I F I, right. So we saw that if you take T and apply it to a vector with coordinates v1, v2, vn, then the image will have coordinates w1, w2, wm, where w, this column vector w is A times v. So this w1, w2, wm is equal to A times v1, v2, vn for some v1, vn, right. So, but these are the coordinates. So what are these things w1, w2, wm? These are actually vectors in the column space, because A times v1, v2, vm, if you take a matrix and multiply it by a column vector, then this you can ask what are the columns of this. Then the first column of this will be A11 v1 plus A12 v2 plus so on, A21 v1 plus A22 v2 and so on, v1 v2 vn, m1 v1 plus am2 v2. Now you look at this a11, a21, am1, this is the first column of A and it is multiplied by the scalar v1. This is the second column of A and it is multiplied by the scalar v2 and so on. So the first column of A times v1, v2, vm is a linear combination of all the columns of A. Likewise, every column of this is a linear combination of the columns of A. So what you can get here are, sorry, that's all there is, right, there's only one column. So what you can get here is a linear combination of the columns of A. So this is the column space of A. So this is equal to summation wifi, where w1, wm belongs to the column space of A. And the dimension of the column space of A is called the rank of A. So rank of A dimension of column space. And what we see is that TV is isomorphic to the column space of A. So the dimension of the column space of A is the same as the rank of T. So rank of A is equal to rank of T. So if A and B are equivalent, then rank of T is also equal to rank of B, because B is another matrix representing A, but with respect to some other basis. So if two matrices are equivalent, then their ranks must be equal. Okay, and this is why C3 cannot be equivalent to C5, because if you look at this matrix, what is its column space? You just look at all linear combinations. They are vectors whose first I coordinates can be whatever you like, and the remaining coordinates have to be 0. So the rank of Ci is is just I. So Ci cannot be equivalent to Cj unless I is equal to j, because otherwise the ranks would be different. So here we have solved we have solved the questions, two questions that are written down. Right, that if you want to know if two matrices are equivalent or not, you reduce them to this canonical form and you see if the number of ones is the same or not in those canonical forms. And the second question about how many equivalence classes are there, the answer is, well, how many? Minimum. So this I can be anything between 0 and minimum mn. So it's minimum nn plus 1. This is the number of equivalence classes. Okay, one interesting consequence of this calculation is that suppose you start with a non-singular matrix. That means it's, what is the meaning of non-singular? It has an inverse. Okay, so in particular it must be a square matrix. If it's not square, you cannot talk about inverse. And its determinant, another way of thinking about rank is that its determinant should be non-zero. Now, if you look at these operations, non-zero determinant is always preserved. So the canonical form should also have full rank, which means it should be identity. So if you have a non-singular matrix, then by performing row and column operations, you can reduce it to the identity matrix. Clear? You reduce it to its canonical form, but that canonical form has to be identity matrix because of non-singularity. So what is happening here? I am taking my matrix, non-singular matrix A, and then I am doing row operations. So I am doing x1, x2, some different row operations, and I am doing some column operations, y1, y2. So maybe I do 25 row operations and 342 column operations, and I get identity. Then I can rewrite this in the following way. Let me first multiply on the right by y342 inverse. Okay, so I get y342 inverse on the right hand side, and this goes away. Then I write y341 inverse, and then I strike out that, and so on all the way up to y1 inverse. And then I strike out all these, and then here I multiply on the left by x25 inverse up to x1 inverse, and I strike out all these. So what I get is A is equal to this. Okay, now if you looked at these matrices which I had written down, the row and column operations, if you take row and multiply it by alpha, you can take the same row and multiply it by alpha inverse, and that is the inverse of the original operation. If you add alpha times the jth row to the ith row, you can again subtract alpha times the jth row to the ith row. So that's the inverse operation. So and if you interchange the I and jth row, you can interchange it again and get back the original matrix. So all those operations, their inverses were also the same types of operations. So these are again, the elementary matrices. These inverses are also elementary matrices. And so what I am saying is that every non-singular matrix is a product of elementary matrices. Now, here is a small research problem for you to work on in the afternoon. Suppose you take a 2 by 2 matrix. Okay? Now, we know that you can write it as a product of elementary matrices. How do you find these elementary matrices? You start with your matrix and then do row and column operations and reduce it to the identity. Maybe I will do an example. So, let us start with a matrix. Zero, 3, 5, 2, and then I want to reduce it to a canonical form. So, first what I will do is I will try to get a non-zero entry here. Okay, so, here is a non-zero entry, let me just bring it over here. So, I will interchange the maybe I will interchange the first two rows. Okay, so this is equal to 5, 2, 0, 3. Okay. Now, what I will do is I will make this 5 a 1. So, what I will do is I will do 1 by 5, 0, 0, 1, and then I will get 1, 2 by 5, 0, 3, and then I want to make this 0. This is already 0, so no work there. I want to make this 0. So, I must subtract from the second column 2 by 5 times the first column, but this anyway is 0, so nothing happens. But here I will be doing what is it? I keep getting confused. So, I want to take 2 by 5. Oh yeah, columns, right? So yeah. So so I want the first column to be the same, and from the second column I want to subtract this, and then this goes away. And finally, I could do either row or column. I will just multiply the second column by 1 by 3. And I get the identity. So, so this original matrix A, which I started off with, satisfies this identity. In other words, so A can be written as, so first I will write this inverse, then I will write this inverse. So, this inverse is 3, 0, 0, 1. This fellow's inverse is 1, 2 by 5, 0, 1. And then I will write this guy's inverse 5, 0, 0, 1, and then this guy's inverse, which is itself. So, here I have been able to write A as a product of 4 invertible matrices. So, I did not have to take 25 and 342, just 4. So, my question for you for the afternoon is, how long can this take? What is, for every matrix, let me try to do it in the least possible steps. Okay? How many can that least possible steps be? Of course, you know, if you hire me to reduce your matrix and you pay me by the number of hours I spend reducing it, then I can take millions of steps. I can, you know, I can just keep instead of subtracting 2 by 5, first I can subtract 8 by 5, and then I can add something and subtract something and so on. But let us look for the shortest possible thing. And so, what I am asking is, for a non-singular 2 by 2 matrix, how many, what is the largest number, what is the maximum number? Some matrices, if you start with the identity matrix, then you need 0 transformations, or if you start with this matrix, you need just 1 transformation, interchange the 2 rows. So, what is the maximum number of number, what is it? It's I am asking what is the maximum of the minimum. Okay, so Now let me define it more carefully. Let L of A be the minimum number such that A can be written as a product of L of A elementary matrices. Okay? And what I am asking you is, what is the maximum possible value of L of A for a 2 by 2 matrix? So, I do not know, maybe this matrix I could do it in 4, maybe somebody can write down a way to do it in fewer steps. Can you see a way to do it in 3 steps? Is this matrix, can you write this matrix as a product of 3 elementary matrices? So, I do not know if you noticed, if you multiply these two, you will get 15 0 0 1. So, this matrix is actually equal to, oops, oh, it is not right? Ah, then it does not go, okay. So, here, yes, okay, good. So, I could not do it as 3. So, maybe it is not so easy. If that was 3 0 0 1, then I could have combined those two. I was thinking it looks a bit odd that I took so many steps to do it. So, yeah, so maybe but maybe there is some other way, somebody cleverer than me could have done it in 3 steps. So, these are the issues you have to think of, and if by some chance you are able to do the 2 by 2 case, I would urge you to try the 3 by 3 case, which is a little harder. Okay, so those are the problems I want you to think about in the afternoon, and now let me just lay the groundwork for what I want to do next time. So, we can now what we did is we allowed ourselves to change the basis of V and the basis of W independently. That means, we chose some new basis for V and we chose some other new basis for W. Now, let us look at linear transformations from a vector space V to itself. So, we are looking at T from V to V, same vector space. And now we have a basis here E1 En, and here also we have the same basis E1 En. And now let us see what happens if we change this basis to F1 Fn or E1 prime to E1 prime. So, suppose I have E1 prime En prime equal to, so I need my notes because I always forget which way I transform the things. Equals E1 En times x. Then I also have E1 En is E1 prime En prime times x inverse, right? Because you just take this identity and multiply it on the right by x inverse, then you will get here times x inverse, here times x inverse, which is identity. So you will get, to get back E1 En from E1 prime En prime, you need to do the inverse. So then what you get is, if the basis for T with respect to E1 En is A, then the matrix basis for T with respect to E1 prime, E2 prime, En prime is x A x inverse, right? This B, this y which we had last time has been replaced by x inverse. So just the same calculation that we did now says that B is x A x inverse. So now we have only one vector space and we are changing its basis, and we want to know whether two different matrices represent the same linear operator on this vector space with respect to different bases or not. This is a different notion of equivalence, okay? And this time determinant is preserved. Determinant of B is determinant of A. So you can't expect so few canonical forms because the determinant can be anything. So you won't get a finite number of canonical forms. So now this is called the similarity relation. So A is similar to B if and only if B is equal to x A x inverse for some, of course, non-singular matrix X, because I have already written down x inverse. And the question is, same questions. Can you find, if I give you two matrices A and B, can you tell me whether they are similar to each other or not? So we will say A is similar to B. So just to get you started on this, here's a question. Is this matrix similar to this matrix? And of course you could keep trying various things and changing it and so on, but it may be a bit, you won't know that the reason you have not got this matrix, whether it is because you just haven't tried the right things or whether you have, they are not similar. So what I want is an algorithm, some way to determine whether two matrices are similar or not. And again, there is something called the rational canonical form which helps decide this problem. So you reduce each of these matrices to what is called the rational canonical form, and then you will be able to see if the rational canonical form is the same, you will say okay, these matrices are similar. If it is not the same, you will say okay, these are not similar. And you will also get a description for the number of equivalence classes. In this case, the number will usually be infinite unless you are working over finite fields, which is what I do. But if you are working over real numbers or complex numbers, then the number will be infinite. So more interesting than asking how many equivalence classes are there, we could ask, can you give me a description of all the equivalence classes? Can you give me some parameterizing set for all the equivalence classes? And we will do these things in the next lecture, hopefully. So with that, it's probably just a little early, but I think this is a good place to stop. And maybe if you have some questions, this is a good time to ask questions, clear your doubts. No questions?